Hello and welcome again to Introduction to Wireless Communications. My name is Yasir Ahmed. The topic we will be covering in this lecture is Introduction to Wireless Communications. Let us first look at the history of wireless communications. Maxwell proposes a mathematical framework for EM waves in 1861. The telephone is invented in 1876. Hertz showed that electromagnetic waves exist in 1887. Marconi proves the feasibility of radio communications in 1895. The cellular concept is born at Bell Labs in 1947. Bell Labs patents its mobile communication system in 1972. Motorola introduces a small mobile phone, Dynatag, in 1973. Advanced Mobile Phone System, or AMPS, the world's first standardized and fully automated commercial cellular service, is deployed in Chicago in 1983. Development of wireless communications has taken two parallel paths. The first is the TDMA-FDMA path that was adopted in Europe, and other one is CDMA path which was adopted in the USA. However, these two paths have now converged towards one global 4G standard known as LTE, or long-term evolution. The major building blocks of this 4G standard are OFDM-MIMO air interface and an all-IP core. We will discuss these in detail in a later lecture. This slide shows the progression of wireless standards and the data rates they offer. As we can see, the peak data rates have increased from 153.6 kilobits per second to 3 gigabits per second in the last 15 years. Which is a 20,000 times increase. On the other hand, the bandwidth has increased from 1.25 MHz to 100 MHz, which is only an 80 times increase. But it must be noted that 1.25 MHz is shared between several users in a CDMA system. Modern wireless communication systems can provide spectral efficiencies of up to 30 bits per second per hertz, as opposed to earlier wireless communication systems which could provide only a few bits per second per hertz. We have used the terms FDMA, TDMA, CDMA in previous slides, but what do they mean? These are schemes by which multiple users can be served by a network over the same geographical area. FDMA and OFDMA separate the users based upon frequency, whereas TDMA separates users based upon time slots. CDMA is a bit complicated, as CDMA users may have the same time slot and frequency, but can be distinguished based upon the unique code. Another important concept is that of frequency reuse. All wireless communication systems use frequency reuse in one way or the other. Let's take the example of GSM system, where a frequency band is divided among 7 cells, known as a cluster. The same frequency band is used in each cluster such that no neighboring cells have the same frequency. Although this is a good scheme to avoid interference between two users using the same frequency channel, it reduces the system capacity since each cell can only have 1/7th of the frequency band. For example, let's look at the GSM system, which has a downlink frequency band of 25 MHz from 935 MHz to 960 MHz. Let's assume that out of this 25 MHz, only 21 MHz can be assigned. This 21 MHz is divided among 7 cells, giving a bandwidth of 3 MHz per cell. We know that GSM channel has a bandwidth of 200 kHz. So 3 MHz divided by 200 kHz gives us 15 GSM channels. GSM also uses time division multiple access. So within 200 kHz, we have 8 time multiplex channels. So the total number of GSM channels is 15 into 8, which is equal to 120 users. So each cell within the cluster can serve 120 users. So if we are talking about this central cell with the frequency F1, it can have 120 users. Similarly, F2 also has 120 users. So for 7 cells, we have a total of 120 into 7, which is equal to 840 users. So the point to note is that in 7 cell reuse, one cell can only serve 120 users, whereas if the whole band was assigned to a single cell, we could have served 840 users in the same geographical area. Modern wireless communication systems use a frequency reuse mechanism called soft frequency reuse. In this scheme, a major chunk of the frequency band is allocated to the central portion of the cell, and a smaller portion is used at the cell edges. Now the frequency allocation for cell edges is done such that no two neighboring cells have the same frequency. This scheme results in higher utilization of the available spectrum. Thank you and see you again.